In this video, I want to discuss a few additional example problems for this topic. So this is a supplement to the videos already recorded and posted. So the topics covered by Chong. So the problems and the materials are taken from this USICO guide, the part on introduction to tree algorithms. So I find this is excellent resources. So you can read it here. They also have a link to a competitive programming handbook. There's a section on tree algorithms. And it has a number of problems, so I took two of the problem here for this supplement lecture. So first, let's recap the definition of a tree. A tree is a graph, and there are several equivalent ways of defining a tree. So a tree, if a graph is connected, and the number of edges is one less than number of nodes, then it has to be a tree. And a graph is a tree if and only if between every pair there is exactly one path between them. So then that also means it has to be connected. And another equivalent definition is it's connected and doesn't contain any cycles. So these are equivalent. The description of problem may use any one of these, and when you see them, you know we are dealing with a tree here. A leaf is a tree. A leaf in a tree is a node with a degree 1, and sometimes the tree is rooted. So there is a one node that we call is the root of the tree. In that case, the root, if it has a degree 1, it's not considered a leaf. But again, that will depend on the problem. So given a tree, you can root the tree at any node. So you can arbitrarily choose a node to be the root, and then you will have a tree structure. So a lot of time, the first step to solve a programming problem with tree is you choose some node and then root it. Sometimes you choose any node. Sometimes there's a particular node that you want to use as a root. So sometimes we're dealing with a star graph, and there are two kind of star graph. So I guess so the first kind is the condition is only one node has a degree greater than 1. So you should think about what this graph look like. So yeah, so I think this is pretty easy. The graph has a one center node, and this center node is connected with all the other nodes. So there's one node have a degree. This will be n-1, and then all the other nodes have degree 1, and then all the other node is connected with this star shape. So another kind of star graph is only one node has a degree greater than 2. So then that means we have multiple nodes. We may have a multiple node with degree 1, but also multiple node with degree 2. So essentially, if all the nodes have if no node has a degree greater than 2, then that means we have a line. So the two endpoint has a degree 1, and all the nodes in the middle have degree 2. So essentially, this degree less than or equal to 2 means we have a single line. So when only one node has a degree greater than 2, that means there is one center node. And then from this center node, we can go outside, basically have this line going out. So, but this line may have length more than 1. So unlike the previous one, all the going out from the center have the path is length 1, but here this can be arbitrary length. So there is a center, and then from the center we can shoot out different lines. So that's this kind of special graph. A forest is a graph. so that every connected component is a tree. So there's no cycle. So essentially, there's no guarantee that all things are connected, but at least there's guarantee that nothing, there's no cycle in the graph. So when every node is disconnected, that's also a forest. That's a special kind of forest. When we root the tree, then we have the concept of parent and ancestor and the children. So every node other than the root will have a parent. So this is the first node. If we go from this node to the root node, that path has to be unique by the property of the tree. So then the first node there, it's a parent. The root doesn't have a parent. So sometime in the code, we will set the parent of the root to be -1. And the ancestor of a node includes its parents and its parents' ancestors. Yeah, and typically a node also is considered its own ancestor. So a subtree of a node are all the nodes that are kind of below this node. If once we define ancestor, we can define those as all the nodes that have n as its ancestor. And this node is typically considered to belong to its own subtree. The depth of a node is defined at its distance from the root. I think very rarely there may be problems where you want to use the you want to have a depth of the largest depth in the tree among any all the nodes, and then you can call that as level 0 or level 1, and then everything else can have a value based on that. But oftentimes, but that is also determined by the distance from the root, and then the deepest child, the deepest leaf in the tree. Okay, so we'll stop now, and next we'll look at the example problem.